All right, good morning, everyone. I hope everybody is doing well in this times. I think we're going to go ahead and get started here, get little introductions going on, and get Richard right into the meat and taters of what's really going on. So I thank everyone, first of all, for attending the Buckley Airxchange webinar, which is titled Understanding the Efficiency of Energy Recovery, Standards, and Climate Zone Revisions, along with a quick overview of how we can implement airflow measurement after the presentation. My name is Mike Hagel. Been 18 months now. I've undergone some massive training on our control products, which you'll see on the screen what we have here, which includes Ebtron. So after the Airxchange presentation and questions that you need to address with what Richard is going to go over, I'm going to briefly talk about application, how airflow measurement can work hand in hand with the new codes and standard changes. So, and you'll see my contact information there, so feel free to give me a call or email with anything that you have, and I'll make sure to get the questions answered for you. Richard is a Senior VP of Sales and Strategy at Airxchange. Happens that Airxchange is one of the largest North American manufacturer of energy recovery fields and plates. Richard currently supports a wide variety of manufacturers, which is OEM, helping them integrate Airxchange components into high efficiency systems. He started with Trane over 30 years ago, has gone to hold senior leadership positions with Munters, Smart, and now Airxchange. Voting member of ASHRAE 62, holds a patent for dehumidification wheels used for energy efficient ventilation and humidity control. He's got a mechanical engineering degree from Georgia Tech and MBA for Emory. So at this time, I'd like to turn over the presentation to Richard. And Richard, thank you.
Thank you, Mike. And thank you, everybody, for taking the time to call in for this meeting. Today, I'm going to be understanding energy efficiency for energy recovery devices. The agenda is I'll go over different performance metrics and applications of energy recovery and how those metrics affect understanding the efficiency of a device and the efficiency of systems. I will review the changes in the various standards and codes that have occurred and are about to have been implemented in 2020. I'll review the lifetime cost impact of proper maintenance or improper maintenance. So the first thing I'll talk about are the different codes and standards that are applicable to energy recovery or mention energy recovery. And the first one that was developed was called ASHRAE Standard 84. This is the method of test that is used for all energy recovery devices to define how they perform. And that method of test was developed in the 1990s. From that method of test, AHRI 1060, now the AHRI 1060 2018 version, was developed in early 2000s to create a certification of manufacturers for energy recovery of their performance. So this is to basically provide a quality control to the people that manufacture energy recovery systems and components. The way that works is that AHRI takes a blind test from the participants in the program to ensure their compliance. In 2020, that AHRI 1060 program was improved to allow the certification of software, which is a more complete measurement of all the points that energy recovery devices can be operated under. In 2011, Guideline V was published by AHRI, and this guideline defines a lot of other system efficiency metrics that I'm going to go over today. From that, you get the code writing standards from ASHRAE that use different parts of the efficiency metrics or the performance metrics from the AHRI 1060 program. So ASHRAE Standard 62 uses some performance metrics that come from AHRI 1060, and ASHRAE standard 90.1 uses a lot of the efficiency metrics that come from standard 1060. From that, you get then the building codes. So the building codes then take what are the ASHRAE code standards and implements or copies or adopts portions of these two codes and uses them directly into the building code. So that's kind of how they all flow together and are used in conjunction with one another. So the first thing is the certification program. You can get from the certification program all of the performance that's certified by the people, the manufacturers that participate in the program. You have to participate in the program, it should go without saying, but you have to participate in the program to get a certification, which means your device or product is independently tested, and again, it's done as a blind test. So the AHRI 1060 will call a participant and say, we want you to send certain models to an independent test site, and we'll validate that performance. The things that are validated with regard to AHRI 1060 energy recovery are these conditions. And what's validated is a peak heating or a peak cooling condition and a variable map condition. And the peak heating and cooling conditions are specified here. In addition to that, the performance can be measured at a balanced or an unbalanced flow. The air pressure drop across the device is certified. And the performance as it relates to leakage, or what's specifically called exhaust air transfer ratio, at different pressure ratios. And I'll explain that as we go forward. But these are all the things that are measured in the 1060 program. And the things I want to talk about are the things that affect energy efficiency. So the first thing that we'll understand is that the map of performance was added in the 2020 program. And what that means is that the participant is subject to a test anywhere on this map. So in addition to a single peak heating or cooling condition, another map condition is selected at what could be an off-peak condition, at a off-peak cooling condition, an off-peak heating condition, or an unbalanced airflow. And one of the reasons that AHRI 1060 adopted that is so that software then could be certified. And so in 2020, we have what's called a transition year. So the manufacturers who participate in the program can choose one of three paths for 2020. The first path is called Path A. This means that the manufacturer has certified his performance and his software, and now that software is listed in the AHRI directory. And it'll say version XYZ in the directory under that manufacturer's name. And what that means is that the performance that comes out of that software at any of those map conditions is certified. It'll carry the AHRI logo. The other two paths are Path B and Path C. So as the manufacturers go through and update their software, they haven't able to release a certified piece of software, they'll be in either Path B or Path C. So Path B basically says that they're going to certify the software by the end of 2020, but they haven't done it yet. They can only certify, the only point that is certified for performance, though, is the peak heating or cooling condition. Selection software outputs cannot carry the logo. Path C for a manufacturer is they're in the process of doing this certification for their software, but they don't plan to have it done by the end of the year. Again, the only point that they can claim, those manufacturers can claim, is the peak heating or cooling condition, and you can't have a software output from that manufacturer that carries an AHRI logo that's not a peak heating or cooling condition. So that's what's going on as it relates to software. One of the important things about having software performance is now the manufacturers of components or ventilation, energy recovery ventilation systems can be integrated into total system performance, so a unitary rooftop unit or an air handling unit, and now start to make system selections that are certified. So the first thing that we're going to talk about that affects efficiency of an energy recovery device is something called exhaust air transfer ratio. Most people would think of exhaust air transfer ratio as leakage. So as you can see, there's arrows moving here, air that's captured in a wheel during what goes. This is the balancing flow amount that is characteristic of any wheel. And every wheel has a slightly different 5,000 CFM, 100 CFM. So the value of outside air correction factor here is 1.04. Again, in this example, the thing that is getting specified by most schedules is the net outside airflow that has to go to the space. So that's 4,800 CFM. That's not necessarily, though, the maximum flow that a fan has to operate at. So that's where you get the impact to energy efficiency. And so what's the relationship to these things? And it's plotted in blue. On the right-hand y-axis, I have outside air correction factor plotted in red. And across the bottom is a sample fan operating cost that range from basically 0 to 15%. And so what you see here is that as exhaust air transfer ratio goes down, the consequence is an increase in outside air correction factor. And you'll have some kind of transition or crossover point at any given design pressure ratio that's generally somewhere between 1 and 3%. That is kind of the optimum point that will have about a 3 to 5% impact on fan operating costs. As exhaust air transfer ratio is driven down for a given pressure differential, the outside air correction factor will go up. So you'll start to increase the amount of fan energy that you use. So as I note here on the slide, this is at 2 inches of pressure differential. I didn't quite explain that in the last slide, so I'm going to go back one. Pressure differential of 2 inches, an example I had there, means that the pressure in this air chamber here at X2 is 2 inches higher at a specific pressure differential. So if this were 1 inch, that OACF would also be lower. So that's kind of the energy impact of leakage, outside air correction factor, and fan design, or I should say pressure differential on an energy recovery device. The changes, and the reason this is important, in 2019 version, the term recirculation and added the term exhaust air transfer ratio, since this is a very specific technical and measured term. It also recognized, as a point of clarification, that the little bit of exhaust air transfer ratio that occurs in a system is not intended to be counted as the ventilation amount of air. And then the last thing is it delineates is that this all should be selected at the design pressure differential. And so you should be able to get any and all of this information from participants in the AHRI 1060 program and use that in your specifications and understand it as it comes to flow balance. So when you get to a flow balance and you want to understand how much air am I really delivering to the space and how much air am I exhausting and how much air is going through the system, what are the different energy measurements? So these are the amounts of energy that are recaptured from one airstream into the other. The first term that most people are aware of, P recovery ratio. Again, this measures the amount of energy that's recovered. Recovered efficiency ratio. This tries to measure the amount of energy that's recovered as it relates to how much air pressure, the amount of energy it takes for the air pressure to overcome the air pressure drop in or through the component. And then the last things, try to keep them straight, but all of this is summarized at the end, and you can get, I have a reference document, something slightly different. The first thing is effectiveness. So effectiveness is the term that's used by AHRI is the measurement of the change in energy or the capture of energy as it relates to the ratio of the flow that's not corrected for leakage. The net effectiveness is a value, and that effectiveness value that's corrected for the beneficial effects of leakage or exhaust air transfer ratio. So what I mean by that is if there's a little bit of leakage occurring here, 1, 2, 3, 4, 5%, whatever that value is, it will make this enthalpy or this temperature or latent condition will improve it over what it would otherwise be if you subtracted out the little bit of leakage that occurred. So the thing to understand about effectiveness is the term that's been around for about 25 years. It was originally the term that's used in ASHRAE net value, and the net values for effectiveness are a term that has now come about is something called enthalpy. It's just the change in enthalpy of X1 that occurs from X1 to X2 over the gross change in enthalpy of the system, which is X1 over X3, or the enthalpy that occurs in X1 and X3. So that's the gross value on the denominator. You can see here there's no flow ratio. It's just a change in enthalpy That's what enthalpy recovery ratio is. Enthalpy recovery ratio is a brand new term. It was established by AHRI in 2016. It's meant to understand the preconditioning effect of an energy recovery device. It's a gross value. There's no adjustment for exhaust air transfer ratio. And as the ratio of exhaust air to supply flow is less than 1, as that ratio goes down less than 1, then enthalpy recovery ratio will also decrease. And I'll show you why that's important in a second. So the changes to AHRI 1060 and 90.1 were meant to clarify the actual differences in the languages between the two standards. So what I mean by that is effectiveness. The term effectiveness was used in both AHRI 1060 and ASHRAE 90.1 prior to 2018 to describe something slightly different. They used the same term, but they actually used a different formula to calculate the value of effectiveness. So in the standard 90.1 and 2016 and earlier versions, you can see here the term effectiveness. And you can see that this is supposed to be 50%, and it's a ratio of the enthalpy in the numerator and the gross enthalpy in the denominator. In the 2019 version, effectiveness was replaced by the term called enthalpy recovery ratio. Now effectiveness is replaced, it's called enthalpy recovery ratio, and in addition to that, for non-transient dwelling units, residential units, apartment buildings, the heating value for enthalpy recovery ratio has changed from 50% to 60%. The point here, though, is that the efficiency term changed, but the formula to calculate it did not. And the reason it changed was because the term was confusing between the 1060 standard and the 90.1 standard. So this is an attempt to clarify the terms so that everybody understands what they're really getting. So let's think about what happens in a practical. Supply airflow are the same, so the ratio is 1. The calculated value for effectiveness and the calculated value for enthalpy recovery are the same. You get the exact same number if you have a balanced airflow. In the second case, where the exhaust value, the exhaust flow is higher than the supply flow, the values that you get for effectiveness and enthalpy recovery ratio are the same. No problems, no clarification needed. Why would you change it? The reason that you would change it is because most buildings that use an energy recovery device have a lower exhaust airflow than the supply airflow. And in these cases, the value that you get for effectiveness is actually different and higher than you would get for enthalpy recovery ratio. And so for this very important reason, when you're trying to comply with a building code that says it should be 50% and you're using two different formulas, you may have a misinterpretation of what really means to comply. Like I said, the standard 90.1 didn't change its formula, it changed its term. It was always intended to be calculated in example 3 here to be 56.9, except that it was asking for a term that may have been coming from AHRI 1060 that was different. So going forward, terms that you should be asking for from a supplier of energy recovery devices is enthalpy recovery ratio as a means to comply to the building code. So effectiveness is no longer used to ensure compliance in standard 90.1 2019. Enthalpy recovery ratio is really the term you should use, okay? The fourth and one, enthalpy recovery ratio as a value will be lower than effectiveness. Effectiveness, however, is a certified AHRI 1060 term, or I should say condition. Enthalpy recovery ratio is not a certified value, okay? But the amount of energy that's recovered is certified. So the actual performance of energy recovery it's certified as effectiveness, but you can see the calculation is slightly different. So what are the practical relationships of different energy terms for energy recovery devices? The first thing that, as we'll start as a practical matter, is the recovered energy as expressed from enthalpy recovery ratio or effectiveness and flow. So you'll start with frequently a design. You'll select something at a 2000 CFM in this case, and it'll have an enthalpy recovery ratio of 80. For a specific device size at a starting point, now as you increase that airflow across that device, the enthalpy recovery ratio will go down. So just a basic fundamental relationship between flow, a specific size, and enthalpy recovery ratio. The next thing to think about is, okay, what happens to the calculation or the actual practical results of a device at a specific airflow and size? So you selected a device, it has an 80% enthalpy recovery ratio. It, in this case, would have an air pressure drop of 1 inch, okay? But that air pressure drop is too high, you want to stay with the same size. As you try to reduce the air pressure drop across that device, and you can do that by taking, in essence, media, recovery transfer media out of a device, you can lower the air pressure drop, but because you have less transfer media in the device, the enthalpy recovery ratio or effectiveness will go down. So these are kind of just some basic guidelines of what happens in a device. As you start to think about size, right, in the case of a wheel, so wheel diameter isn't a measure of performance. And to prove that point, I've given you 3 examples here from AHRI certified data. So the first one is an Airxchange 52-inch wheel. So we have a 52-inch wheel at 3,000 CFM, has 75% enthalpy recovery ratio. I have another 52-inch wheel here in purple. At 3,000 CFM, it has about a 67 enthalpy recovery ratio. So same size wheel, different enthalpy recovery ratio. So again, size is not a measure of performance. Right? Similarly, I have a 66-inch wheel here from a different manufacturer, and at 3,000 CFM, it has about 73% enthalpy recovery ratio. So you can see this wheel had to be bigger. And so from this picture here, if you were trying to match performance in a retrofit or a design application, you'd have to build it for a bigger wheel to achieve the right performance. So wheel diameter is not a measure of performance, it's a measure of size, right? And the other thing to keep in mind here is like, where do these things run out as it relates to the minimum enthalpy recovery ratio required by code? So you can see here the difference here between these wheels is the less efficient wheel will have a maximum flow that's limited by the code at about 5,500 CFM, whereas the other wheels can perform down up to about 8,000 to 9,000 CFM and still achieve the minimum building code requirement. So again, relationships, understanding of efficiency and energy recovery to practical aspects. The other things that we're going to talk about now are the other measurements of system efficiency. So the first one is recovered efficiency ratio. As I mentioned, this is a ratio that tries to understand the amount of recovered energy to the power consumed due to the air pressure drop of the component. So the general formula is the first one, specific terms of it. So you then take the air-to-air heat exchanger, its net total capacity, and you divide it by the amount of power it takes to overcome the air pressure drop of the device. That's the power in the blowers, so the fans, the additional power needed to overcome the air pressure drop, and then the power of a motor to turn, in the case of a wheel, to turn a wheel. In the case of an enthalpy plate, you wouldn't have this power of that motor. And so this allows you to get a value for something called recovered efficiency ratio. Recovered efficiency tried to help you understand different air pressure drops. So it has an air pressure drop of 1 inch. In this calculation, its RER would be 50. As the air pressure drop goes down by about 0.2 of an inch in each increment here, the RER increases from 50 to 70 in the case of option B. It goes from 70 to 90 in the case of option C. You can see where the air pressure drop is being reduced from 1 inch to 0.515. And in the last case, the air pressure drop is increased by 0.6, and the RER is now more than double what it was to start with. So this helps you understand just the relationship of the value to air pressure drop and how it's really driven by air pressure drop and not really enthalpy recovery ratio. So understanding RER, it is not used. I controlled for enthalpy recovery ratio in the example I dropped in a device. You're probably reducing the amount of recovered energy. Anyway, the other thing to think about is combined efficiency factor. So again, in guideline V, it then creates a measurement of a system, a unitary system, in conjunction with an energy recovery device, and how you calculate system efficiency. So it's called combined efficiency factor. So it's the net cooling or heating capacity divided by the power consumed. It's a single point measurement. It's a measure of the total power. It actually, you can simplify this to use an RER value and an EER value of a unitary device, or COP in the case of other systems or heating. And then the other important thing here is the amount of load each one of these devices contributes to the system capacity. That's probably the most important thing here, because as you have a certain efficiency for RER and ERR, the intuition here is that the RER value is always higher than the EER, even though they have the same units, BTUs per watt. But if you're trying to drive a bigger portion of the load, Y, to the highest efficiency component, RER. So CEF. CEF is a measure of total system efficiency of combined systems with an energy recovery device of energy to be consumed by the higher efficiency component in order to increase system efficiency. This building code, it's not a certified point, it's not in standards, but it is in AHRI guideline V if you want to get more details on it. So what I wanted to help you understand, so you don't have to go through all those calculations, is a sensitivity of these different metrics to changes in their values. So the first thing I did here is I took a recirculating system that's 30% outside air, 70% recirculated air, and I calculated the CEFs, which are highlighted here in both matrix. Yellow means that it's increased the base system by at least 15%, and green, light green, means it's increased the base unitary EER by at least 25%. In the case of enthalpy recovery ratio, I held constant the air pressure drop at 1 inch across the change, the increase in enthalpy recovery ratio. In the case of the RER matrix, I decreased the air pressure drop, as I started with, from 1 inch to 0.4 inches in order to get the resultant CEF values. And what you see here is that the starting point of efficiency of the enthalpy recovery ratio increase in RER, even if achieve the same levels of system efficiency in enthalpy recovery ratio. What happened? Plate. In this case, you've removed the motor from the wheel energy consumption, and consequently, and pretty dramatically, but in a 3070 system, you've actually got no change in the system efficiency. It's actually within the margin of error. It doesn't show up in the improvement in system efficiency. So basically no real change in the CEF in this system design. The more commonplace that systems, though, are your energy recovery outside air systems. Portion of the energy, and again, same kinds of relationships here. Constant air pressure drop, decreasing air pressure drop for the two matrices. The light green is a 25% increase, and the dark green is a 50% increase over the base system. Again, starting at the base point, but as we increase the enthalpy recovery ratio, and even if we increase the enthalpy recovery ratio by only 10 percentage points, which is fairly modest, you can get a system CEF of 25. Whereas you don't get to 25 on this, say, this unitary device that has a starting point of 17, even with 110 RER. So again, the RER value has less impact in and of itself, its increase in and of itself, because of air pressure drop reduction on the total system efficiency.
Hey, Richard, we lost you.
Is the enthalpy recovery component. And the more of that load that gets done by the energy recovery component, the higher the system efficiency. And only the highest possible system efficiencies occur with the highest possible enthalpy recovery values. High RER values in and of themselves aren't necessarily making a big impact on system efficiency. The best system efficiencies occur at a 70% enthalpy recovery ratio and an air pressure drop not greater than 1 inch. The other thing that, so I've finished kind of the matrix of all the terms. The other thing that's outside of the system that does impact how much energy gets recovered or how efficiently it gets recovered is climate zone. So ASHRAE has done climate zones. Many of you have probably seen this before. And what I'm going to show you here is 3 different wheels that Airxchange makes that have fairly good enthalpy recovery ratios, and we're gonna model them for different regions. So Boston, not surprisingly, is dominated by heating recovery that Airxchange makes. They're within 3 or 4% of each other in efficiency, but there is a slight difference in the amount of energy they save relative to each other. So the right-hand set of columns is relative to each other, the amount of energy they save, and it takes into account the negative effects of air pressure drop. So the far left-hand one, the Airxchange EFX, is the highest air pressure drop, highest efficiency device. The next one is a little bit lower air pressure drop, a little lower efficiency, and the next one is the lowest air pressure drop and a lower enthalpy recovery ratio. In the 4th column, this is the competitor wheel that I've been using in the example that has a lower, even lower enthalpy recovery ratio, but it has a high RER because the air pressure drops are really low. And you can see as they relate to each other, this is noticeably less in total energy savings. Not surprisingly, when you look at savings, and you can see that actually starts to shift which one of these wheels makes the most sense. Again, the low enthalpy recovery are still Alice, which is kind of a mix of both heating and cooling savings. Again, you get a shift now to kind of the middle option here from Airxchange, and again, a low enthalpy recovery ratio and a high RER value still doesn't, still isn't the most efficient. It plays an important factor in the characteristics of a wheel. The last thing I would say is obviously wheel allows you to maintain the energy recovery, and that's particularly true with enthalpy recovery devices. So Airxchange makes a device that is segmented, really easy to take out of the unit, really easy to clean. This is an example from a video that was on LinkedIn by a service contractor. What we have seen in the site surveys that we've done in retrofit replacements is if you can't clean a wheel, the decrease in yearly performance is about 2 or 3% per year. In this example, in this particular project at Georgia Tech, they could actually surface clean this. They were vacuuming these wheels off, but they still were getting a degradation in, that was noticeable in their energy recovery performance. And it was so noticeable that they ended up replacing all 30 wheels on their campus because they couldn't sufficiently clean it beyond just a surface cleaning. And some of those wheels were only about, and you see this wheel here, this does not look like a bad wheel. It's still in good condition, but it was losing a noticeable amount of energy because they couldn't do a full cleaning on it. This is another project here where with wheels that are segmented and easy to maintain, the replacement and the best dilution as measured by CO2 in the casino that they've ever recorded, and they measure and track CO2. So retrofits are something that a summary for this whole presentation. I should say, for a lot of the energy recovery parts of this presentation, you can download from our website under white papers. So if you need some of this information for a quick reference, this is a really good summary for you to use, and you can get it there. And with that, I'll turn it back to.
Thank you very much, Richard. I appreciate it. Wow, that was a lot of good information, detail with what's really going on with standard changes and for submit. We appreciate your time. What I want to talk about a little bit and not take too much of your time is about the you've heard things like exhaust airflow ratio, outdoor correction factor, enthalpy recovery ratio. A lot of good information but you ask yourself, well, oh, that's great. How are we going to measure that? Well, Ebtron has a fantastic probe with the RH sensor that calculates enthalpy dew point for you with the transmitter. So with the energy recovery, with the energy recovery ratio, not only do you have airflow to the wheel to and fro, you can get an enthalpy calculation based on the new RH sensor that they have in their probe. And on the screen, I'm just giving you a overview of the transmitter with the new RH sensor. Here's the specifications to it. I'm just going to really go over the RH portion here. Not only is the RH a good application, you also have temperature with thermal dispersion. You've got airflow. Now with the RH, you got enthalpy calculation and dew point that you can read and pick up from that monitor to ensure and validate your ratio that you're in compliance at any given time. The RH sensor has a barometric pressure sensor, and it's a weighted average to be accurate, so that you can ensure that the calculations that they're doing is really accurate, so that you can go on and make sure that your energy recovery system is doing what it's supposed to do. And this is important and critical, because once it leaves the factory and everything is tested, that's wonderful. But how do you validate it in the field? With the Ebtron system on your energy recovery, you can not only validate, but you can measure constantly and trend to ensure that your energy recovery is meeting the expectations of AHRI, ASHRAE, for any of the code or standards that you can do. Some of the thoughts that I'd like to kind of go over a little bit. Validate your system after leaving the factory. Retrofits. Some customers may call and go, man, my unit's not performing like it should. Well, if you have an Ebtron system on there, you can say, well, show me some trend data, so you can see exactly when that wheel was beginning not to perform. And just like Richard mentioned, maintenance is king. So you can see, you know, with the airflow going in and out and the pressure drop higher, you'll know if the wheel is being clogged or the filters are changed. So it's important after it leaves the factory that you have a system in place that you can validate what's going on at any given time. Outdoor airflow measurement. Talked about outdoor correction factor. This is really awesome, because not only do you have an accurate outdoor air coming into the wheel, with the supply, you can ensure what is really going on. If it's greater than 1 or less than 1, as Richard talked about earlier on the ratio. Great precision in airflow, and Ebtron has different applications for your systems of whatever you want to need for the calculations to ensure that your system is working as you've designed, or want the owner to ensure that he's getting exactly the amount of outdoor air that he needs and not over ventilating or under ventilating. Here's my contact information. Please feel free to give me a call with any questions, concerns. Be glad to help. If you guys want to look at some of your design specs, I can help you with that to ensure that you got the product that you want for the validation. And Ebtron, I think, is really good and a good fit for everyone for what we've done. So if you guys have any questions, that's pretty much sum it up. We appreciate your time for the Airxchange Buckley webinar. And again, my contact information is on the screen. Feel free to give me a call or email. Be glad to answer any questions that you have. We're happy to help. And we have a lot of people at Buckley that can help you with any designs, concerns, or choose a product that will fit your needs. Does anybody have any questions? If not, I'll wait on just a little bit longer. The last webinar, I exited out a little too quick. So I'll hang on just a tad here to see if you guys have any questions. Appreciate your time, and thank you.